Talking about the weather forecast is a great way to start a friendly conversation. The weather forecast matters to us. It tells us what to wear in the morning, it tells us what to pack for a trip. And we also know that weather forecasts can sometimes be wrong, but we'd be foolish to ignore them when they tell us something big is heading our way. Climate models, on the other hand, tell us that by the end of this century, if we carry on burning fossil fuels at the rate that we have been doing, and we carry on cutting down forests at the rate we have been doing, the planet might warm by somewhere between 5 to 6 degrees centigrade. Now that might not seem much, but put it into context. In the entire history of human civilization, the average temperature of the planet has only varied by about 1 degree. So that forecast tells us something big is coming, and we probably ought to pay attention to it. But on the other hand, we know that weather forecasts don't work the longer into the future we peer. Tomorrow's forecast is usually pretty accurate. 3-day and 5-day forecasts are reasonably good, but next week, no, they always change their minds by the time that week comes. So how can we peer 100 years into the future and look at what is coming with respect to the climate? And so should we trust those forecasts, and should we trust the climate models that provide them to us? 6 years ago, I set out to find out. I'm a professor of computer science. I study how large teams of software developers can put together complex pieces of software. I've worked with NASA, studying how NASA builds the flight software for the space shuttle and for the International Space Station. I've worked with large companies like Microsoft and IBM. My work focuses not so much on software errors, but on the reasons why people make those errors, and how programmers then figure out they've made an error and how they know whether to fix it. To start the study, I visited 4 major climate modeling labs around the world, in the UK, in Paris, in Germany, Hamburg, Germany, and in Colorado. Each of these labs have typically somewhere between 50 and 100 scientists who are contributing code to their climate models. And although I only visited 4 of these labs, there are another 20 or so around the world, all doing similar things. They run these models on some of the fastest supercomputers in the world, and many of the models have been in construction. They've been building the model for more than 20 years, the same model for more than 20 years. When I started the study, I thought I would ask one of my students to attempt to measure how many bugs there are in a typical climate model. We know from our experience with software, there are always bugs, right? Sooner or later, the machine crashes. So how buggy are climate models? More specifically, what we set out to measure is what we call defect density. So basically, how many errors are there per 1,000 lines of code? And by this measure, it turns out that climate models are remarkably high quality. In fact, they're better than almost any commercial software that's ever been studied. They're about the same level of quality as the space shuttle flight software. So here's my results. The actual results, you'd have to read the paper. So we know it is very hard to build a large, complex piece of software without making mistakes. We know even these models, even the space shuttle flight software had errors in it. So the question is not then, is the software perfect for predicting the future? The question is it good enough? Is it fit for purpose? And to answer that question, we'd better understand what the purpose of a climate model is. Now, first of all, I probably ought to say what a climate model is not. What it is not is a projection of trends that we've seen in the past extrapolated into the future. If you did that, you'd be wrong because you haven't accounted for the underlying causes. You haven't accounted for what actually causes the climate to change. And so the trend might not continue. They're also not decision support tools. A climate model can't tell us what to do about climate change. It can't tell us whether we should be building more solar panels or more wind farms. It can't tell us whether we should have a carbon tax. It can't tell us what we ought to put into an international treaty. What it does do is it tells us how the physics of planet Earth work and what the consequences are of changing things within that physics. I could describe it as computational fluid dynamics on a rotating sphere. So here's a here's a model of planet Earth, and it rotates, and it has gravity and so on. And I'm calculating what's going on in the atmosphere and the oceans as it rotates. But computational fluid dynamics is kind of complex. I went into my son's 4th grade class recently, and I started to explain to them what a climate model was. And the first question they asked me is it like Minecraft? And you know what? That's not a bad place to start. So if you're not familiar with Minecraft, it divides the world up into blocks, and the blocks are made of stuff. They might be made of rock or metal or water or wood or whatever, and you can build things out of them. There's no gravity in this world, so you can build floating islands, and it's great fun. So climate models are a bit like that. What you do if you want to build a climate model is you divide the world into a number of blocks. And the difference, of course, with Minecraft is that the blocks are made of stuff. In a climate model, the blocks are really blocks of space through which stuff can flow. So in each block, what you want to know is this a block of air? Is the air flowing that way or that way? Once it's left this block, which block is it going to next? Is it going up? Is it going down? You have to keep track of where it's going next and tell the next block there's something coming in there. If there's air in this block, we also have to count for, well, is there dust in that air? Is there water? Is there humidity in there? How much? What's it doing? Where's it going? We have to account for the sun during the day warming that up. And of course, some of what's in this block might block some of the incoming sunlight. If there are clouds or dust there, some of the incoming sunlight might not get down to the blocks below. During the night, or actually at all times, there's also heat escaping. So we ought to account for heat passing up through these blocks and whether anything in the blocks blocks that heat. Again, for example, clouds and greenhouse gases would block that heat as it leaves the block. Now, as you can see from the diagram here, this shows you, the blocks are pretty large. This one shows you blocks of 87.5 kilometers on a side. That's pretty big. If you want more detail in the model, you have to make the blocks smaller. And some of the fastest climate models today look more like that, about 30-kilometer blocks. Ideally, you want to make the blocks as small as possible. But of course, as soon as you do that, you have many, many more blocks that you have to keep track of. So you get to the point where the computer just can't run that fast. A typical run of a climate model, if you want to simulate a century's worth of climate, you might wait for a couple of weeks on some of the fastest computers in the world for that run to complete. So the limit is how fast do our computers go? And that limits how small we can make the blocks. But doing it this way is remarkably successful. What I want to do is show you a video of what a climate model can do today. So this is a simulation showing a year's worth of weather from a climate model. And what you're seeing clouds, and the orange bits are where it's raining. And for comparison, I want to show you satellite data for the whole of the year 2013. And if you look at the two side by side, you can see many of the same patterns. You can see the westerlies, the winds at the top and the bottom, heading from west to east, and then nearer the equator, you can see the trade winds flowing in the opposite direction. If you look very closely, you might even see a pulse over South America and a similar one over Africa in both models. That's the daily cycle as the land warms up in the morning and the water evaporates from the soils of the plants, and then later on in the afternoon, when it cools, it turns into rain and drops back down on there. So the bottom is an actual year, it's 2013. The top is not a real year at all. It's a typical year. So it doesn't correspond exactly. So you won't get storms forming at the same times in these two, because they're not designed to be an exact simulation. The climate model is designed to get the patterns right. And by and large, it does. So, how do you build a model like this? The answer is, of course, very slowly. It takes a lot of time. It takes a lot of failure. One of the things that amazed me when I visited the labs is that the climate modelers don't build these models to try and predict the future. They build these models to try and understand the past. And they know their models are approximations. They know, they frequently quote, as a famous quote by the statistician George Box, who said, "All models are wrong, but some are useful." What he meant by that is that any model of the world is only ever an approximation. You can't get all the complexity of the real world into a model. But even so, a simple model is a really nice way to test your theories about the world. So the way that the modelers work is they spend their time focusing on places where the model doesn't quite work right. And so they might say, okay, well, this model right now isn't getting the Indian monsoons right. It might be getting the amount of rain about right, but it's dumping it on the wrong place. And they'll form a hypothesis. They'll say, well, I think we can improve the model because I think this particular process is wrong. And if we improve that in the model, we think that will fix our simulation of the monsoon cycle. And they run an experiment where they've got the old version of the model they knew was getting it slightly wrong, and the new version, and they run a whole series of experiments to test whether the hypothesis is correct. And then, if after a series of experiments they believe their hypothesis is correct, they then have to convince their colleagues, they have to convince the rest of the modeling team that this is actually an improvement to the model. But in other words, in order to build the models, what they're doing is they're doing science. They are developing hypotheses, they're running experiments, and they're going through a peer review process to convince their colleagues that what they've done is correct. The climate models also have a few other weapons up their sleeve. Imagine for a moment if Microsoft had 25 competitors around the world, all of whom were attempting to build their own versions of Microsoft Word. And then imagine further that every few years those 25 companies all got together and said, we're going to agree to run all our versions of Microsoft Word on a very complex battery of tests designed to test all the different conditions under which you might expect a word processor to work. And not only that, they're going to agree to release all of the results of those tests to the public on the internet, so that anybody that wanted to use any of that software can pore over all of the data and find out how well each version did and decide which they want to use for their own purposes. That's what the climate modelers do. No other software in the world is built in that way. There is no other software for which there are of the order of 25 teams around the world trying to do the same thing and competing with each other. They also have another weapon, which is that climate modeling, in some sense, is a lot easier than weather forecasting. And to explain what I mean by that, I better show you. So, imagine for a moment that I have a water balloon. Actually, you don't have to imagine, I have a water balloon. And I'm going to throw it at, let's see, I'll probably reach about the 5th row there. So I'm going to throw it at the 5th row. You ready? Now, you'd like to know who's going to get wet, right? So if you were able to measure everything about my throw, you know, am I throwing it overarm or underarm? Which way am I facing when I let go of it? How much swing did I put in? If you could measure all of those aspects of my throw, and you understand the physics of how objects move, you could come up with a fairly accurate prediction of who, let me just see who, so who is going to get wet. That's like weather forecasting. You have to measure the current conditions as accurately as possible and then project forward to see what trajectory it's moving in. And of course, if I make any small mistakes in my measurement of my throw, those mistakes will multiply as the balloon travels further. And the further I attempt to throw it, the more inaccuracy there will be in my estimate. So that's like weather forecasting. Any errors in the initial conditions multiply up quickly. And the current limit appears to be about a week or so. Beyond that, the errors just get so big that we can't make accurate predictions. I'm not going to throw the balloon. Okay. Now, in contrast, climate models would be more like releasing a balloon into the wind and predicting where it goes by knowing about the wind patterns. And I haven't got any wind here, so I brought my own. Okay, so here's a balloon, and imagine I was to release this into the wind. Now, that balloon's going to bob around there in that wind pattern, and I could leave it going, I could come away and come back tomorrow, and it's still going to be doing the same thing. If the power stays up, I could leave it there for 100 years, and it's still going to be doing the same thing. I won't be able to predict exactly where that balloon is going to be at any moment, but I can predict very reliably the space in which it will move. I can predict the boundaries of its movement. And if the things that shape those boundaries change, I know what the factors are that shape those boundaries, I can tell you how the patterns of its movement are going to change. I can tell you how the boundaries are going to change. So we call that a boundary problem. The initial conditions are almost irrelevant. And after a while, it doesn't matter where the balloon started. What matters is what's shaping its boundary. So, can these models predict the future? And are they good enough to predict the future? The answer is yes and no. We know the models are better at some things than others. They're better at predicting temperature change than they are at predicting change in rainfall, for example. We also know that each model tends to be better in some areas and weaker in other areas. And if you take the average of a whole set of models, you get a much better simulation of how the planet's climate works than if you look at any individual model on its own. What happens is the weaknesses in one model are compensated for by the other models that don't have those weaknesses. But the results of the models have to be interpreted very carefully by somebody that knows what they're good at and what they're not good at. So you don't just take the output of the model and say, that's how it's going to be. Also, by the way, you don't actually need a computer model to predict climate change. The very first predictions of what would happen if we keep on adding carbon dioxide to the atmosphere were produced over 120 years ago. That's 50 years before the first digital computer was invented. And those predictions were pretty accurate. In fact, what has happened over the 20th century has followed very closely what was predicted all those years ago. Scientists also predicted, for example, that the Arctic would warm up much faster than the equatorial regions, and that's what happened. They predicted that nighttime temperatures would rise faster than daytime temperatures, and that is what has happened. So what do the models do? The models just add some detail to what we already know about the climate. They allow us, for example, to explore what-if questions. So you could ask of a model, what if we were to stop burning all fossil fuels tomorrow? And the answer is, from the models, it looks like the temperature of the planet stays about whatever temperature it was when you stop. If we wait 20 years and stop, whatever temperature we're at that point, we're stuck with for tens of thousands of years. You could ask a model what happens, flip it the other way, what happens if we dig up all of the remaining reserves of fossil fuels, all the coal, all the oil, burn it all at once in one big party? Well, the planet warms up far more than we would like. More interestingly, you can ask of a model something like, well, what if? What if we attempt to block some of the incoming sunlight to attempt to cool down the planet to compensate for the warming we're getting from adding greenhouse gases to the planet? And there have been a number of very serious proposals to do that. There are some that say, well, we should float giant space mirrors. Well, that might be a bit hard, but there's a simpler way of doing it, which is you put dust up in the stratosphere, and that blocks some of the incoming sunlight. And it turns out that if you do that, you can very reliably bring the average temperature of the planet back down to whatever you want just by adjusting the amount of this dust that's there. Unfortunately, some parts of the planet cool down too much and other parts of the planet don't cool down at all, and everybody's weather patterns get messed up. So in other words, it seems like that could be a solution, but when you study the model results in detail, you know what? There are too many problems with a solution like that. Remember also that, as I said, we know pretty much what's going to happen with the climate without needing a computer model. And the computer models just add detail to what we already know is going to happen. If they're wrong, they could be wrong in either direction. They might underestimate climate change just as much as they might overestimate it. And if you look at how well the models can simulate the past few decades, especially the last decade, you'll see some of that going on. For example, the models have underestimated how fast the Arctic ice has melted. The models have underestimated the rate at which the sea levels have risen over the last decade. On the other hand, they've overestimated the rate of the warming at the surface of the planet. On the other hand, they've underestimated the rate of warming in the deep oceans. So some of the warming is going to a different place where the models thought it would go. So they can just as much underestimate as they can overestimate. Okay, so when you see a graph like this, which comes from the latest IPCC report which just came out last month. It doesn't tell us what to do about climate change, it tells us the consequences of what we might do. Remember, people aren't represented in this model in any way whatsoever, except with respect to us producing greenhouse gases and adding them to the atmosphere. That's the only way people show up in these models. If we keep on increasing our use of fossil fuels, finding more oil, building more pipelines, digging up more coal, we'll follow the top path. And that takes us to a planet that by the end of this century is somewhere between 4 and 6 degrees warmer, and it keeps on over the next few centuries getting warmer and warmer. The bottom path, on the other hand, the dark blue, this is what would happen if we, year after year, from now onwards, only ever reduce the amount of fossil fuels we're using as a global society. If every year we use a little less than we did the previous year, till about mid-century when we get down to 0, and we also then have to invent some way to start removing that carbon dioxide from the atmosphere before the end of the century. And that's how we might get to follow that lower path. The model doesn't say which of those we should follow. It just says, well, if this is what you do, this is what the climate will do in response. So you could say then that what the models do is they take all of the data and all of the knowledge that we have about the climate system and how it works and put it into one neat package, and it's our job to take that knowledge and turn it into wisdom, to decide what to do from here on and which future we would like. Thank you very much.